In this video, we will discuss some higher order derivatives. Before we do that, let's try to understand the derivative also as a function, right? Basically, you are starting from an arbitrary function, right? Let f here be a function, right? It's a function, which means that's a rule, right? For any x, you get some output, which is f of x, right? And we choose x here be in the domain of f, right? So whenever you have something in your domain, you can calculate the limit of which give you the derivative, right? So just evaluate this limit as h goes to 0, f of x plus h minus f of x over h, right? That's a limit, right? Because x is in the domain of this function, we can evaluate such a limit. If such a limit exists, so the derivative exists, you get a new number, which is called f prime of x. When we say the limit exists, we mean limit exists as a finite number, right? So if the limit exists, right? So you put all the x whose derivative exists together, you get a new function, which is called f prime, right? So which is also a function, right? As a new function. So for any x, if the derivative exists, you apply our new function f prime, you get f prime of x, right? So f prime is also a function, right? So the domain of this new function, domain of f prime, equal to all the x such that f prime of x exists. The limit exists, you get this new function, right? So you can see that the domain of this new function could be same as the domain of f, or sometimes you have to get rid of a few numbers, right? Maybe there are some numbers the derivative does not exist, right? We'll see examples. We will see examples in a different video where the derivative doesn't exist, right? Let's see some notations for this developed by different mathematicians, and sometimes one is convenient, sometimes the other one is convenient. So you can use f prime of x to represent this new function, or y prime, or dy over dx, or df over dx, or capital D f of x, or capital D x f of x, right? All these notations means the same thing. We are evaluating this special limit here, right? That's the same meaning. After you have this new function, you can try to evaluate corresponding limit again, right? So f double prime of x is f prime of x, then prime. So what's the meaning of that is as h goes to 0, f prime of x plus h minus f prime of x over h, right? This is called the second derivative. And if you get second derivative, you don't need to stop here. You can get third derivative, right? And x is equal to f, the derivative of the second derivative, right? Prime here, so this is same as h goes 0, f double prime of x plus h minus f double prime of x over h, right? You can do it again and again. For example, the fourth derivative, we don't want to use we don't want to use the prime angle because there will be 4 primes. We use a number in a parenthesis to represent that is our fourth derivative of this function. So this is basically the derivative of the third derivative of this function, right? And in general, we write down f n here of x to be the nth derivative of f, right? So from here, this part are called the higher order derivatives, right? From the first, second, third, and you can go on and on, right? So let's see a quick example, easy example, right? We are given the function f of x equal to x squared plus 2, right? We want to find f prime of x, f double prime of x, and f triple prime of x, right? Clearly, you can see that you cannot directly go to calculate the third derivative. You have to start from the first, then go to the second, then go to the third, because the definition only allows us to do one derivative, right? Step by step. So let's try to calculate f prime of x first. So this is equal to, as h goes 0, x plus h squared plus 2 minus x squared plus 2. So f of x plus h minus x squared plus 2 and over h, right? And so this is equal to, as h goes to 0, right? You try to cancel the numbers and squares. You get 2 times hx plus h squared over h, right? Because 2 will be canceled, x squared will be canceled. So this is, take out the common factor h from the numerator. You get this is as h goes 0, h 2x plus h over h. So h canceled. Now you can plug in 0, right? You get 2x, right? Now we are ready to evaluate the second derivative. So f double prime of x, this is as h goes 0, you get what? You get this is f prime of x plus h minus f prime of x over h. So this is as h goes 0, you get 2 times x plus h minus 2x over h. So this is, you try to simplify the numerator, you get 2h over h. So this is 2, right? The last third derivative, this is x. So this is equal to, as h goes 0, f double prime of x plus h minus f double prime of x over h, right? Now you can see that for the second derivative, that's a constant. No matter what's the input, output is always 2. So this is, as h goes 0, 2 minus 2 over h. So 0 over h is always 0. So this is 0. So this is how do we evaluate the higher order derivatives. And then if you are given a more complicated function, you can do this also to get first, second, and third derivative. This is a fundamental way to get the derivatives.